Mercury, the smallest and innermost planet in our solar system, offers a unique glimpse into the extremes of planetary environments. Named after the Roman messenger god due to its swift orbit around the Sun, Mercury has captivated astronomers and scientists for centuries. Despite its close proximity to Earth, it remains one of the least explored and understood planets in our celestial neighborhood. This exploration is not just an academic exercise. It provides critical insights into planetary formation, evolution, and the extreme conditions that can exist on other worlds. Mercury orbits the Sun at an average distance of about 57.91 million kilometers, 35.98 million miles, completing one orbit in just 88 Earth days. Its orbital eccentricity is the highest of any planet in the solar system, meaning its distance from the Sun varies significantly over the course of its orbit. This eccentricity leads to interesting phenomena, such as periods when Mercury is closest to the Sun, perihelion, and farthest from the Sun, aphelion, which significantly affect its surface temperatures. Mercury's rotational period is another fascinating aspect. The planet rotates on its axis once every 58.6 Earth days, resulting in a unique 3-2 resonance between its rotation and its orbit. This means that Mercury completes 3 rotations for every 2 orbits around the Sun. Consequently, a single day, night cycle on Mercury, one solar day, lasts 176 Earth days, leading to prolonged periods of daylight and darkness. The surface of Mercury is a testament to the violent history of the solar system. It is heavily cratered, much like Earth's moon, indicating that it has been geologically inactive for billions of years. This ancient, scarred landscape provides a window into the early solar system, preserving the record of impacts and volcanic activity from a time when the planetary system was still forming. Prominent surface features include the Caloris Basin, one of the largest impact basins in the solar system, spanning about 1,550 kilometers, 960 miles, in diameter. The impact that created this basin was so intense that it caused seismic waves to propagate across the planet, forming a region of jumbled terrain known as weird terrain on the opposite side of Mercury. In the long term, the possibility of human missions to Mercury, while currently far-fetched, cannot be entirely ruled out. As our technological capabilities advance, we may develop the means to protect astronauts from the extreme conditions and enable short-term visits for scientific exploration and research. Such missions would require revolutionary advances in spacesuit design, habitat construction, and radiation shielding. These technologies would not only have to provide protection from the searing heat and frigid cold, but also offer sufficient radiation shielding to protect against intense solar radiation. Furthermore, establishing temporary shelters or mobile bases that could move to shaded regions or be anchored in more temperate zones during specific times of Mercury's rotation would be crucial. Exploring Mercury with human presence could yield unprecedented scientific insights. Direct geological sampling and in situ experiments could provide more detailed information than what is possible with robotic probes. Understanding the planet's core, its magnetic field generation, and its surface composition would enrich our knowledge of terrestrial planet formation and evolution. Moreover, the data collected from human missions could improve our understanding of how to build more resilient life support systems and habitat structures that can withstand extreme environments, benefiting long-term human space exploration goals, including potential missions to Mars and beyond. The challenges of a human mission to Mercury would also drive innovation in spacecraft design and mission planning. The proximity to the Sun means that spacecraft would need advanced thermal protection systems to survive the intense heat and radiation during transit. Innovations in propulsion technology would be required to navigate the Sun's gravitational pull effectively. The lessons learned from overcoming these challenges could accelerate the development of future deep space missions and enhance our ability to explore other extreme environments within our solar system. Ultimately, the endeavor to send humans to Mercury would be a testament to human ingenuity and the relentless pursuit of knowledge, pushing the boundaries of what we consider possible in space exploration. Mercury also exhibits significant tectonic activity in the form of lobate scarps, steep, cliff-like structures that can extend for hundreds of kilometers and rise up to 3 kilometers, 1.9 miles, high. These scarps are thought to be the result of the planet cooling and contracting over time, causing the crust to buckle and break. Mercury's lack of a substantial atmosphere means it cannot retain heat, leading to some of the most extreme temperature variations in the solar system. During the day, temperatures can reach a scorching 430 dC, 830 dC, 810, due to the intense solar radiation. However, without an atmosphere to trap this heat, nighttime temperatures plummet to around 180 dec, 290 def. This dramatic temperature fluctuation spanning over 600 dec, 1100 ref, poses a significant challenge for any form of life or robotic exploration. Mercury's atmosphere is so thin that it is essentially a vacuum. This exosphere, composed mainly of oxygen, sodium, hydrogen, helium, and potassium, is constantly being replenished by solar wind and micrometeorite impacts. The lack of a substantial atmosphere means there is no weather, wind, or clouds on Mercury, and the sky would appear perpetually black. Despite its small size, Mercury possesses a magnetic field, although it is much weaker than Earth's. This field is likely generated by a partially molten outer core, similar to Earth's geodynamo mechanism. Mercury's magnetic field interacts with the solar wind, creating a magnetosphere that provides some protection from charged particles. However, the magnetosphere is not strong enough to shield the planet from intense solar radiation, adding another layer of harshness to its environment. Imagining a human being on Mercury, even for just 5 seconds, brings to light the incredible resilience and vulnerability of the human body. The immediate and most pressing concern would be the lack of breathable air. Without a supply of oxygen, a person would lose consciousness within seconds due to hypoxia. Brain damage would begin almost immediately, and death would follow shortly thereafter. The extreme temperatures present another lethal hazard. During Mercury's daytime, the intense heat would cause third-degree burns almost instantaneously. The body's core temperature would rise rapidly, leading to hyperthermia, heat stroke, and death. At night, the frigid cold would induce hypothermia in seconds, with the body's extremities freezing first, followed quickly by the core. Additionally, Mercury's lack of atmospheric pressure would cause a condition known as ebullism, where bodily fluids would begin to boil at normal body temperature due to the lack of external pressure. This would cause immense pain, swelling, and severe internal damage. The lack of pressure would also result in rapid decompression, further exacerbating the physiological trauma. Surviving even 5 seconds on Mercury would necessitate advanced technology far beyond what we currently possess. A specialized spacesuit would be indispensable. This suit would need to maintain a stable internal environment, including temperature regulation, breathable air, and protection from radiation and micrometeorites. The suit would have to be constructed from materials capable of withstanding extreme temperatures, with advanced insulation to protect against the thermal extremes of Mercury's surface. Active cooling and heating systems would be essential to regulate the wearer's body temperature, preventing hyperthermia and hypothermia. Radiation protection is another critical aspect. Mercury's proximity to the sun means it is bombarded with high levels of solar radiation. The suit would need to incorporate advanced shielding to protect against ultraviolet rays, X-rays, and other forms of harmful radiation. Additionally, it would require a robust communication system to maintain contact with a base station or spacecraft, as well as life support systems to supply oxygen, and remove carbon dioxide. The psychological impact of being on Mercury, even for a few seconds, cannot be overstated. The alien and hostile environment would be profoundly disorienting and frightening. The sight of a black sky with an enormous, blazing sun could induce extreme stress and anxiety. The knowledge that the external environment is lethal would add to the psychological burden, potentially leading to panic or shock. Moreover, the isolation and sensory deprivation experienced in such an environment could have severe psychological effects. Humans are accustomed to the presence of an atmosphere, the blue sky, and the familiar sounds of Earth. The stark silence and visual strangeness of Mercury could trigger feelings of loneliness, fear, and disorientation. Exploring the idea of spending 5 seconds on Mercury opens up a range of theoretical considerations and thought experiments. For instance, what if we could extend the duration of exposure? Could we develop technology that allows humans to stay on Mercury for longer periods? What scientific discoveries could be made by studying Mercury up close, and how would they benefit our understanding of the solar system? One thought experiment could involve the logistics of a manned mission to Mercury. How would we transport humans to and from the planet? What kind of infrastructure would be necessary to support such missions? The challenges are immense, but so are the potential rewards in terms of scientific knowledge and technological advancement. Developing such missions would push the boundaries of our engineering and scientific capabilities, leading to innovations that could benefit life on Earth as well. Given the extreme conditions on Mercury, robotic exploration has been the primary method of studying the planet. NASA's Messenger mission, which orbited Mercury from 2011 to 2015, provided invaluable data about its surface, composition, magnetic field, and exosphere. The spacecraft was equipped with a suite of scientific instruments designed to withstand Mercury's harsh environment, including cameras, spectrometers, and magnetometers. Robotic missions allow us to explore Mercury without exposing humans to its lethal conditions. These missions can gather detailed data, map the surface, and analyze the planet's geology and magnetic field. Future missions, such as the European Space Agency's Bepi Colombo, will continue to build on this knowledge, providing more comprehensive insights into Mercury's characteristics and evolution. The scientific discoveries made through the study of Mercury have far-reaching implications. Understanding Mercury's geology and composition helps us learn about the formation and evolution of rocky planets. The planet's heavily cratered surface provides clues about the early solar system, including the frequency and intensity of impacts that shaped the planets. Mercury's magnetic field is another area of significant interest. Studying its origin and behavior can provide insights into the geodynamo processes that generate magnetic fields in rocky planets, including Earth. This knowledge is crucial for understanding the conditions necessary for a planet to sustain a magnetic field, which plays a vital role in protecting a planet's atmosphere and potential habitability. The extreme temperatures and lack of atmosphere on Mercury also offer a natural laboratory for studying the limits of material science and engineering. Developing technologies to withstand these conditions can lead to advancements in materials science, with potential applications in various industries on Earth.